that. So I will talk about the Coulomb branches, and so this talk is about examples of Coulomb branches. So I gave a mini course last week about the Coulomb branches, and I will give a quick reminder of that. And anyways, I will not use the detail of the lectures last week, so you don't need to know what are the precise definitions and what are their properties. I only briefly remind you the most basic one afterwards. So anyways, I defined the Coulomb branch for pairs of G and M. G is a complex reductive group. M is a symplectic representation of G. And in last week, I assume M is of this form, N plus N star. N is a complex usual representation, and N star is its dual representation. And N plus N star has a natural symplectic form. Then I define the Coulomb branch, which is denoted by MC of G of M. And this was defined as a spectrum of certain commutative ring. And so this is affine algebraic variety. And this commutative ring is defined by using convolution product on some infinite dimensional variety. So except this is infinite dimensional, the construction is very similar to what Eric explained yesterday. And one big difference is the ring which you define by convolution product is non-commutative usually, but in this special case, you get a commutative ring. So this is something special. And if you are familiar with geometric Satake, then this commutativity is you can also see the commutativity in geometric Satake because commutative geometric Satake says that in the category of Barbash on the affine glass Manian is isomorphic to the representation of the dual group, and the product, monoidal structure is a tensor product, and this tensor product is commutative. So anyway, as I said, you don't need to remember the detail of the construction. And I also explained what is called Hicks branch, so which is much easier to define. So you just regard M as a symplectic manifold, and G is a Hamiltonian. You regard M as a Hamiltonian G manifold, and you take the symplectic reduction or Hamiltonian reduction. So you take the level set of the momentum map, which in this case I implicitly assume the level set I take 0. You take inverse image of 0 and take categorical quotient by G. So this is the definition of symplectic reduction. So for given pair G and M, you assign two varieties. One is Coulomb branch, the other is Higgs branch. And I also discussed example last week. So those G and M, which arise from quivers. So you choose quiver and you choose two graded vector space B and W, finite dimensional complex vector spaces V and W. So which, and then you consider, from that you define G and M. This is exactly the same as Eric's talk yesterday. So I will not recall what it is, but you will see what is GM in a slightly different situation later, so I don't need to recall the precise definition. So anyway, the Hicks branch in this case is what I called quiver variety. So I introduced this in 1994. And then I also explained, when the quiver is of finite type, then the Coulomb branch is some variety which is closely related to geometric Satake. And, but it makes sense for arbitrary quiver. And then you can consider geometric Satake using Coulomb branch for those examples coming from quiver. And then I briefly mentioned that this is regarded as an example of phenomena called symplectic duality by Braden-Rickert and Webster. So this construction, so you get the representation, integrable highest weight representation of Kac-Moody. This is still conjecture, maybe. I should emphasize that. So we have conjectural construction of the integrable highest weight representation of Kac-Moody algebra from the Coulomb branch, which should be regarded as symplectic dual to my old construction of Kac-Moody representation on the middle degree homology group of slightly modified Hicks branch, which chi is a character of G, and you take, instead of categorical quotient, you consider the geometric invariant theory quotient. So anyways, I think so far we do have a better understanding of Coulomb branch, which arises from this quiver. And we really want to somehow enlarge our knowledge, so we should study more examples. So this example is somehow related to nilpotent orbits, and because of that, I think this example is very interesting. So I first recall what we know in quiver is of type A. So I consider this kind of quiver. So these numbers are dimensions of vector spaces. So graded, so you decompose into according to quivers. And this is, I think, the standard notation. So then, quiver variety in this case is known to be of this variety. So it's OB bar is a nilpotent orbit for some general linear group. I don't specify which the rank of general linear group, but so this is nilpotent orbit closure of type A, and S lambda is slice. It's slightly different from the Slodwy slice, but anyway, so this is a variant of slice of Slodwy. Slice to another orbit. And the two orbits, lambda and mu, are specified by those dimensions, B's and W's, by this combinatorial expression. So you don't need to remember these formulas, but somehow, anyway, you just accept that there's some combinatorial expression starting from dimension vectors. You can assign two partitions, lambda and mu, and then you have Higgs branch is the variety of this type. And here we implicitly assume that mu is actually partition, mu1 is greater than or equal to mu2 and so on. And this is in terms of W's and V's, we assume this condition. And in fact, so this lambda once, so I define lambda and mu by this formula, but conversely, if you have lambda and mu, you can recover V and W by solving these equations. So anyway, we have this result. And for the Coulomb branch, we already know that, so this, again, I take the same G and M for this. Then the Coulomb branch is the similar variety, but you replace the two partition mu and lambda by their transpose. So because all of lambda must be contained in the closure of mu, so you have the dominance or the relation between mu and lambda. Lambda is smaller than mu, but if you take the transpose, the order is opposite. So lambda appears in here, and the mu appears in here after replacing transpose. And this can be shown several ways. I mentioned last week that in this Quiver gauge finite type, and I also mentioned at the beginning of my talk, this Coulomb branch is affine Grassmannian slices. And in this case, by Markovits and Vibornov, this slice is known to be isomorphic to these intersections of nilpotent orbit and the slice. And also, in my joint work with Takayama, we directly show this first I identify the left-hand side with so-called Cherenk's ball variety, and then you can see this isomorphism. So anyway, in type A, we have this kind of understanding. So Higgs branch and Coulomb branches are very similar, and so partitions are replaced by transpose. So we want to understand a similar thing for nilpotent orbit for classical groups, which is realized by using the so-called orthosymplectic quivers. Okay. So I start with examples. So Higgs, as I said, the Higgs branch is much easier to define, and it's much easier to understand. So I start with Higgs branch. So here is a notation. So instead, our quiver is bipartite. So we have plus vertex and minus vertex. Maybe this is important, so I keep it in here. Plus, and I cannot write the numbers inside the circle. So I instead write in here. Maybe not n. Then I understand this to be O of n, and the minus of n, minus of 2n. So my convention is SP is always even. How to say? SP of C. The symplectic vector space is 2n dimensional. And we also framed one. So this means, again, this is ON, but not included in G. So this disappears as in framing. And this is bipartite, and so that if two vertices are joined by edge, then one of vertex is plus and the other vertex is minus. The edge is always connected in this way. So and for the usual quiver gauge theory, we assign bifundamental. So homomorphism from here to here and homomorphism from here to here. But instead, so we just assign the vector tensor product of vector representation, C to N. So this is the representation of OM times SP of 2N. Okay, then so given bipartite graphs with those numbers, you assign. You take just the tensor product of those for each vertex, and the group is the product of groups which correspond to circle vertices. And for square vertex, you don't include those groups into G. But otherwise, it's very similar to the ordinary vertex for circles. So anyway, then so this is a symplectic vector space. So M is here plus vertex has symmetric bilinear form, and for minus we have a symplectic. And as a tensor product, this is a symplectic vector space. And this is a symplectic representation of this group. So I have M and G from that. And then I consider the symplectic reduction. So this is MH. And in these examples, so first example, I start with the 2n dimensional symplectic vector space, and I decrease the dimension one by one. So and at the end, I get one dimensional symplectic, symmetric orthogonal vector space. And then you consider the symplectic reduction. It's known that this is nilpotent cone for SP to N. And in fact, the isomorphism is just, so if this is this component is A, then you consider A star adjoint of A and A. This is an endomorphism of this, and this gives element in the nilpotent cone. So this isomorphism is something explicit, and it is very similar to the case of Quiver variety, when the Quiver variety is a nilpotent cone for type A. And for SO2n plus 1, again it is similar. Start with 2n plus 1 dimensional space, and you decrease dimension one by one until you arrive at one dimensional space. So this is. And the third case, SO of even is slightly different. So instead of decrease one by one, you first decrease by 2 in the beginning. So you go to 2n minus 2. And then after that, you decrease one by one. And that is, of course, you cannot put the 2n minus 1 here because, as I said, my convention, this number is always even for negative, for minus vertex. And this is compatible with the fact that regular nilpotent orbit, so you remember that the nilpotent orbits are corresponding to partitions in type A, and you have the similar result for classical groups, but there are some restrictions for partitions. And for orthogonal groups, even parts appear with even multiplicities, and odd part, for SPs, odd part appears with even multiplicities. That's a well-known classification. So in particular, you cannot put mu equal 2n. 2n is a regular nilpotent orbit for type A, but that is not allowed for orthogonal group. So the regular nilpotent orbit for SO even is this one, 2n minus 1, 1. And because of this reason. And you just compute the difference of those numbers, and then you take it is a partition, and you take the transpose partition. Then it is corresponding these one. So in first case, this is 1, 1, 1, 1, so you get 2n. Second one also. But the third one, you get 1, 1, 1, 1, but at the last, you get 2. 1, 1, 1, 2, and take transpose, you get this one. Okay? And these results, these examples are a special case of what Kraft processes studied in 1982. So it's a long time, 40 years ago. And in fact, they realize all nilpotent orbit closure of the classical groups in a similar manner. Okay? And here, slightly, you must be slightly careful. So this is, when I wrote O, this is, I usually mean that the orthogonal, orbit under the orthogonal group. And orthogonal groups and the special orthogonal groups are connected component of the orthogonal group. And orbits and SO orbits are slightly different. If the partition have only even parts, then it's called very even partitions, and orbits and SO orbits are different. And all orbits consist of two SO orbits. Here, so I'm talking about. I mean, here you don't, all the example is just, there's no difference, but afterwards, if I talk about this O of mu, then in general, I'm talking about all orbits. And in 1994, I also generalized this result to the variety which appears in Quiver variety for type A. So the intersection of orbit closure and the slice. And this is based on a result of Kronheimer. And Kronheimer proved the similar statement for arbitrary nilpotent orbits, but his description of nilpotent, this variety is based on the so-called Nernst equation of some ordinary, he considers ordinary differential equation and take its moduli space of solutions, and he identified it with Kronheimer. And those matrix form is a consequence of so-called Edechim description. And So anyway, so this result is, the proof is the same as the proof which I mentioned in the beginning for type A, which I believe this is well known, but it can be generalized to classical groups. And one remark which will be important and also even in just after Kraft processes this work, they also noticed this, that so here we take the group as in this convention, I take orthogonal group instead of special orthogonal group. So in principle, you can also consider SO of n instead of orthogonal group. Then, so if you replace this S of O. So in some cases, in fact, the quotient becomes isomorphic, but in some other cases, you could get some covers of orbital closure in this Kraft process construction. So this could be, how to say, interesting cover or could be trivial cover. So it depends on the situation. And this is a really delicate problem. But also, I should mention that the Kraft process studied the so-called special pieces. And special piece, I mean, there's a notion of the special nilpotent orbit, and the special piece is a union of the special orbit and the smaller non-special orbit, which is not included in other smaller special nilpotent orbit. So anyway, special nilpotent orbit is realized by replacing some of orthogonal group by special orthogonal groups. So anyway, so the special nilpotent orbits are important in representation theory, so this kind of modification might be really important to be explored. So anyway, this is a small remark. Any question? So.
In this setting, I guess, this Austin duality.
Yeah, I will mention, yes.
In this setting, you don't have the partial
I can, but so usually I take so this is so remember the Quiver variety has two versions, categorical quotient and GI T quotient version. So this orthosymplectic, this version, I only consider the categorical quotient version. But instead, we can first consider the categorical GIT quotient in the usual Quiver variety setting, and I can define the involution on this, and then consider fixed points. That is a candidate of symplectic resolution. But this is not always true. So this is, I mean, in general, so it is known that the orbit closure may not have symplectic resolution. So this is again the very delicate issue. Any other question? So in that sense, somehow, because of these phenomena, I think this example is really interesting and challenging. So now I consider the Coulomb branch. So as I said, this construction is general if you have a complex deductive group. And maybe I should emphasize that this could be disconnected because we are considering orthogonal group. The group could be disconnected. And maybe I don't remind the construction, but it depends on, it uses affine Grassmannian. So affine Grassmannian for this possibly disconnected group is the same as the affine Grassmannian for its connected component, but we are also using equivalent cohomology. Then the equivalent cohomology are different if I replace it by connected component. So the construction depends on particular choice of the group, which could be disconnected or not. So anyway, definition of the Coulomb branch, if M is n plus n star, this is due to my joint work, Brevan and Finkelberg. But for general M, symplectic presentation, this is relatively new development by two groups of people, and the archive numbers are this. they appeared last year. So anyway, I will not recall the definition. So we have we have a definition, and later I will explain. This is not general. You need to assume some condition for G and M, if M is not of this form. So I will explain this condition afterwards. Then the one of most fundamental properties of Coulomb branch is the integrable system. Coulomb branch is equipped with integrable system. MC has a map to T mono W. This is a spectrum of the equivalent cohomology point. So if G is, so usually this is the T mono W, and if G is possibly disconnected, I define while group as by this formula. So for orthogonal group, this is slightly different from the usual while group. So anyway, this is technicality. And you have Coulomb branch has birational isomorphism to cotangent bundle to the dual torus divided by while group. So T is the maximal torus, and this T is a real algebra of T, and T check is the dual torus. So Coulomb branch is always Coulomb branch has a dimension equal to twice of the rank of the group. And because this is birational and this is commutative diagram, the generic fiber of this integral system is T-check. And also I mentioned that if you pull back function from T mono W, then those functions are Poisson commuting. So that's definition of integrable system in the sense of Liouville. So anyway, so these properties, please keep in your mind. So now return back to example, which I mentioned. So starting from some dimension vectors, and you decrease dimension one by one, and for the even orthogonal group, you must be a little careful, but otherwise just decrease by one. So I start with SP of 2, and you decrease by 1, and then it stops here. But so it means this is the gauge group is O1 because number is 1. O1 is G mod 2, so rank is 0. So whatever definition, definition is, I think, the definitive definition. So if you apply the definition of the Coulomb branch, so you cannot get any non-trivial example in the definition, unless you modify the definition in some sense. So dimension is equal to 0, becomes 0. So this you cannot get the non-trivial Coulomb branch. But in this particular case, you can modify the construction slightly. So you consider, instead of O1, you increase dimension by 2. And we don't take O of 2, so we take S of O2. Then SO2 is GL1. And I discussed last week that for GL1, and for vector representation, the Coulomb branch can be computed explicitly. And in this particular example, you can directly check that the Coulomb branch is C2 mod Z2, and which is the nilpotent conform SO3. And in this case, it is the same as nilpotent conform SP2. But also, you observe that the Higgs branch, as I said, this Higgs branch, you have a vector space and you take the symplectic reduction, but because the group is a finite group, you don't need to impose the momentum application. You just take the quotient, categorical quotient. Then you get the same variety, C2 divided Z2, because Z2, also O1 is Z2, and you have two-dimensional vector space, right? So you get the same variety. And because this is a symplectic vector space, you should regard this as nilpotent conform SP2. So you get N of sp2 as a Higgs branch and N of SO3 as a Coulomb branch. And you can go further. So I applied the same modification. Instead of odd orthogonal group, I just replace S of even, increase the dimension by 1, S of 2i. And in fact, this ansatz was found by Guage and Wheaton in 2008. And they observed, maybe I should mention that the Coulomb branch was originally studied in physicists, but we didn't have a mathematical rigorous definition for many years, but physicists already knew many things on the Coulomb. So this is ongoing project with Finkelberg and Hanani is a theoretical physicist. He studied those Coulomb branches in many situations. So anyway, in this case, the Higgs branch is unchanged, so you get the nilpotent Coulomb for sp2n, and the Coulomb branch is S of odd. And so, as I mentioned in the beginning, the relation between the Higgs branch and the Coulomb branch gives an example of symplectic dual pair in the sense of Braden-Lickerton product from Webster. And it is, as far as I understand, symplectic duality is a collection of phenomena. So we still don't have a theoretical understanding. But it is a consensus that nilpotent Coulomb for G and nilpotent Coulomb for the Lagrange dual group are symplectic dual to each other. So anyway, I think this modification is correct in that sense. And for C, this is in fact, if you compute the dimension, you see that this is wrong. But before going to that, in fact, this violates the condition which I mentioned. So for G and M, if M is not N plus N star, there is some condition which we need to impose to define the Coulomb branch. This is the Wheaton's obstruction. So you consider, M is a symplectic representation of G. So you have a map, group homomorphism from G to SP of M. So you consider the induced homomorphism to the fourth homotopy group. So this is plus minus 1, and this must be banished. That is the construct, the necessary condition to define, necessary sufficient condition to define Coulomb branch. So for this, you add, so in this case, you add the dimensions of nearby vector spaces, and this must be even. And if this is 2n minus 3, then this condition is violated. So you need to replace this vector space in even numbers anyway. So then it is natural to replace all odd ones to SO2i. Then you see that both Coulomb branch and Higgs branch are nilpotent Coulomb for SO even. You observe this. And this is already observed by Guage. And so far so good. But for nilpotent Coulomb for SP of 2n, we have slightly different phenomena. And this example is studied, as I said, so Guage Wheaton already studied this example in detail. So SO of odd and start from 3, and the ansatz was just decrease the dimension 1 by 1. And in this case, we consider O of 1 and SP of 2. So rank is 1. So the Coulomb branch is 2-dimensional. And the Higgs branch is nilpotent Coulomb for SO3. So if you believe the symplectic duality, then we should somehow, we want to get a nilpotent Coulomb for SP2, so which is 2-dimensional. So the previous answers, so we replace the odd orthogonal group to SO even, but if I replace this by 2, SO2, then it's not correct. Dimension is not correct. So we don't want to change the dimensions. So we need to understand this example, this choice of dimension vectors. Then, so because this, you assign all 1. So the Coulomb branch is, so you just move this to be framing vector space, and then you divide by G of 2, which is you regarded as Weil group of 1. Then, fortunately, in this example, you can compute this Coulomb branch and also this action. And in fact, this was already done by Wheaton. So this Coulomb branch before quotient is the so-called D2, type D2 surface. So usually people start the n from n equal 4, but at least in the level of the equation, you can still make sense for D2 surface. Anyways, this is the defining equation. And it has 2 type A1 singularities. So D2 Dynkin diagram consists of two points without edges. So it is natural in that sense. But anyway, so you have two type A singular. And D2 action is given by this formula. And so singular point is C and delta equals 0 and eta equals plus minus 1. These 2 points are exchanged by this G2. So starting from 2 type A1 singularity, you get 1 single type A1 singularity. So this is a good sign because we want to have type nilpotent cone for sp2, which is type A1 singularity. But nevertheless, we get a new singular point at C equals eta equals 0. And delta equals 0 because it's fixed by this. So originally it was a smooth point, but because of this involution you get. So it means that the quotient still has 2 type A singular points, and it cannot be the nilpotent cone for sp2. Okay. So it seems we cannot realize nilpotent. I mean, in this particular case, we have other construction with sp2, but if n is higher, it seems we cannot get nilpotent cone for sp2 and as a Coulomb branch for the also symplectic quiver. Any questions? Okay, let me continue. So I will state the main result. Unfortunately, I need I need to introduce various notations to make a precise statement. So the result is little imprecise, but actually we do have precise statement for this result. So suppose Q is linear, or we allow that the cyclic quiver. And if for example, I think maybe I should also give one example. So in particular, we allow Jordan quiver. And this must be even number. And I don't specify the rule for when we have edge loop like this. And in this case, we assign this is skew. No, not skew. Adjoint. Instead of skew adjoint homomorphism. What is homomorphism? So the Lie algebra of SP2N consists of skew adjoint homomorphism, but instead you take this one and tensor with C2 and symplectic form. You put the standard inner product for here, symmetric inner product here, and you tensor with symmetric product here. So the Higgs branch, I'm not sure if anybody studied the corresponding Higgs branch, but that this appears in the ADHM descriptions of the instantons on C2. So anyway, so we could consider the cyclic Quiver case. And so for the group, during the talk, I start with the convention that all the groups is orthogonal group, but at this moment, we only study the case when all the groups are SOs. So we must be really careful when we try to identify the Higgs branch, because we cannot directly apply the Kraft process. But we are talking about the Coulomb branch. So then the Coulomb branch is what we call orthosymplectic Bohr varieties. So orthosymplectic Bohr varieties is defined properly, but it's roughly symplectic reduction of a product of three types of symplectic manifold with Hamiltonian group action. So some example you saw yesterday's Chen's talk, and I think this is this suggests that his duality is something to do with this Higgs and the Coulomb branches. So anyway, we have three types. One is what is given by this. You consider SOM and take product with some specific sliced specific nilpotent orbit of Hooke type. So m minus n and 1n. So this is Hooke type nilpotent orbit. And for Cherok's Bohr variety, which is identified with Coulomb branch for usual Quiver of type A or affine type A, you consider instead of SOM, you just consider the same variety for general linear group. And this is m is greater than n, and if m is smaller than n, you just replace m. And I assume m minus n is odd in this case, because otherwise this violates. So this Hooke partition is not allowed for orthogonal nilpotent, orthogonal group because of this parity reason. So this must be imposed. And for SP, we have 2m to n and similar, very similar. So we have again Hooke partition. And in this case, it is allowed, m is equal to, could be n, and in that case, we define, instead of this, we consider cotangent band of SP to m times vector representation. And we also have bifundamental, like this. So the definition is the same as before. But here, in some cases, it is slightly complicated. In some cases, we take orthogonal group, and for some vectors, vertex, we take special orthogonal groups. So these are chosen appropriately. This is a delicate point. There are two delicate points in the definition, which I don't explain. So this choice of S1O, and also when we have very even. So as I said, for very even orbits, orthogonal orbit and special orthogonal orbits are different, and we must be careful for corresponding. But there are corresponding phenomena for orthosymplectic Bohr varieties, so this must be careful. Okay, unfortunately, I do have some time to explain example. Before that, because of these reasons, so m minus m must be odd in the orthogonal group, 2m minus 2n is always, of course, even. Because of that, and combining those by taking several copies of those building blocks and take the diagonal Hamiltonian reduction, you can describe the sliced marginal nilpotent orbits. But in type A, in fact, we can construct arbitrary slice to arbitrary nilpotent orbit. But for orthogonal and special orthogonal symplectic group, so for mu, partition mu consists only of even parts for symplectic group, because always this difference is even. And for orthogonals, mu consists of only odd parts. So in particular, if you want to try to realize the slice to trivial orbit, zero orbit, then corresponding partition is 1 to m. But of course, this consists of only odd powers. So this condition is violated. So it seems by this construction, you cannot realize T star of SP2M. That is the reason why I mentioned that earlier, that nilpotent cone for SP2N is probably not realized as a Coulomb branch, also symplectic quivers. Okay. So special case. By the way, so up to this moment, I think I gave the very similar talk in satellite conference in last June. So this is a still ongoing project, and we studied more examples, and we have found interesting phenomena, which I want to report. So we consider the special case when the Higgs branch is of this form. So in general, Higgs branch is, after at least for orthogonal groups, that was intersection of nilpotent orbit closure and slices. But we assume that the nilpotent orbit part is a full nilpotent cone. Then in return back to type A, so we replace lambda and mu by its transpose, and then swap the role of mu and lambda. So this, so in type A, if we take the full nilpotent cone, then it means the slice, we take the slice to zero orbit. That means the whole Lie algebra. So you just, so expect that the Coulomb branch is something to do with the orbit closure. So this is the example which you should first consider. But the point is that this transpose, because of this parity condition of the partition, the transpose does not correspond to nilpotent orbit in general. So there's this subtlety appears in this Coulomb branch. And also because of this reason, we should look for the case when the nilpotent orbit is of type SO. So you cannot consider the case when for the nilpotent orbit for SP. So it means the original Higgs branch should be nilpotent. So this variety for SP or SO even. Okay. So we studied this example. And in fact, this Hanani and his collaborator studied this example intensively in 2017. And our current understanding, so this is theorem in quotation marks, so we still need to check something, but I hope this could be established quickly. So Coulomb branch in this case, first you take the so-called Barbash-Vaughan duality. So this is some generalization of this transpose operation, which is cross-related to Lustig-Spartenstein duality. So you get, so this duality sends the nilpotent orbit for SO odd to SP to SO odd. And SO even to SO even. So for SO even, this Barbash-Vaughan is exactly equal to Lustig-Spartenstein duality. And in general, you don't get the closure of this orbit. Instead, you need to take a cover and then take affinization. And in some cases, this variety is not normal, and the Coulomb branch is always normal in this region. So in that case, we should get the normalization. And this covering group could be determined from the given choice of the dimension vectors. And so far we studied many examples, and we always get the so-called Lustig quotient of component group, which is denoted by A bar. Okay, I think I don't want to, let me give, I don't want to record the definition of Barbash duality. So I give examples. So we choose these dimension vectors, and instead of orthogonal groups, I always take special orthogonal groups. Unfortunately, as I said, in Guage to Wheaton's prescription, they somehow replace the odd orthogonal group by special orthogonal group whose dimension is greater by 1. So we do the same for this example. So originally, if you consider this to be, you assign also one-dimensional orthogram G model 2 in this example, you get, you apply my previous old result in 94 to get this result. And you can also show that even if you replace 1 by SO2, you get the same variety. So this is intersection of nilpotent cone with slice to the orbit to 2. And then by using this orthosymplectic ball variety, so the Coulomb branch is affinization of Z2 cover of 312 or 4SO3, SO5. And this 312 is the image of Barbash duality applied to 2. And we have similar example starting from those choice of dimension vectors. And maybe So this corresponding Higgs branch is sliced to 2, 1, 2. So these numbers can be read off from the dimensions of those framing vector space. So 2, this is for 1, multiplicity is 2, and this is 2-dimensional, and so on. So anyway, in this case, you can compute the Coulomb branch. This Coulomb branch is exactly this orbit closure, nilpotent orbit closure. So you see that this orbit and this orbit is the same, right? But only the difference is here you take the G2 cover and affinization, but here this is just the closure. Starting from 2 different orthosymplectic Quiver gauge theory, and Higgs branch, whose Higgs branch are different. So these 2 orbits are different, but the Coulomb branch are very similar up to this G2 cover. They are the same. And the Barbash duality or Spartan-Stern duality is not actually duality. So it's a generalization of transport, but you first take the transport partition and then you consider, so you may not have the corresponding orbit. Then you look for the orbit partition which is allowed and smaller than this fake partition. So this is a combinatorial description of Spartan-Stein duality. So in particular, the operation is not involution. So this Lustig Spartan-Stein duality is nilpotent orbits. Sends all nilpotent orbits for SO or SP to itself. But the DLS square is not identity in general. And D of LS. But it is, if composite 3 times, then this is returned back to original. And the image of this is special nilpotent orbit. And there are bidection for special nilpotent orbit for SO odd and SPs. And Barbash duality is the composition of this identification and the construction which I just explained. let me continue a little bit my example. And this is a simpler example. So again, I increase this dimension from 1 to 2. Then you can also show that in this case, it's the same as the one which you get for orthogonal O one for the Higgs branch. And this is a you regard this as the slide, this variety for SO4, and the partition here is 2, 2. And as I said, this 2, 2 has two SO orbits. So in particular, this orbit closure of 2, 2 has two irreducible components, which I denote by 2, 2, 1 and 2, 2, 2. So they intersect like this. So they share the common point here. So this trivial nilpotent orbit is a common point. And we take either of point in here, generic point in here, and take a slice. Then you see the type A1 singularity. This 3-1 is the regular nilpotent orbit. And in this case, again, because SO2 is GL1, you remember the computation which I gave in the last week. So this Coulomb branch is C2 mod G plus minus 1. So this is the closure of this either of irreducible, either of special orthogonal orbits. So you should not get the union of two A1 singularity glued at the 0 point, right? So you don't get O of 2 bar. Instead, you get one of irreducible component, which is, I think it's interesting. As I said, the Coulomb branch is always normal. So you cannot, so this is not normal variety. So you cannot get this. But somehow, miraculously, Coulomb branch pick up one of irreducible components. And correspondingly, so you consider slightly complicated example. So in this case, Hicks branch is like this, and you compute the Barbash-Bogan duality. And so if you look at the Hasse diagram for nilpotent orbit for this SO9, then you have this partition, and you have the next smaller nilpotent orbit, which is 5, 1 to the 4. And so this, the transversal slice to this was computed by Kraft processes. And in this case, this is A1 union. This example appears. This union of two A1s along the origin. So in particular, if you have such slice in along the next smaller orbit, then orbit closure is not normal. So I should say that the Kraft processes have determined the normality of the nilpotent orbit closure for classical groups, and so in general they are not normal. And in this example, because I think this is somehow related to this phenomenon. So the Coulomb branch miraculously pick up one component, and in this particular example, you can show that Coulomb branch is not the orbit closure, but it's normalization instead. So this is, I think, the general phenomena. We always get to the normalization of the. In general, it could be cover of the nilpotent orbit, but we always get normalization of cover of the orbit. Okay, thank you for attention. I stop now. Yes. Mm-hmm. 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 Yes, yes. You have the Coulomb branch, And you have the, I mean, strictly speaking, we must apply the so-called hyperbolic restriction factor. But in general, so we have a C-star action, which correspond to the stability. So in this symmetry between the Higgs branch and Coulomb branches, so this stability parameter, which I implicitly use in my construction, appears as the mass parameter in the Coulomb branch side. So mass parameter is action on the Coulomb branch. So we consider the C-star action on the Coulomb branch, and we consider the attracting, repelling set for the Coulomb branch, which, I mean, in general, if you flow a point by this C-star action, then it usually goes to infinity. So the picture is like this. So the flow is going like this. So most of the points go to infinity when under the flow. But if this is on this axis, maybe I'm confused with attracting and repelling set, but so if you take a point on this axis, under the flow, it stays, and it converges to the origin, right? The most of the points go to infinity, but some points stay in compact set and eventually converge to the origin. So this is a very general definition. And if you take the repelling set in the Coulomb branch, then it is a Lagrangian subvariety in the Coulomb branch, and it has many irreducible components in general, and that homology, top degree homology of this repelling set give rise the representation of Katsuma-Didi algebra. That is expectation. Mm-hmm. Well, yeah, but yeah, that is true. But I'm not sure this point of view is correct. But this Higgs and Coulomb branch is from 3D gauge theory.
So that statement which you mentioned,
Mm-hmm.
so they were talking about.
Yeah, that is really. I mean, I try to make a distinction between the 3D mirror symmetry and the symplectic duality. As far as I understand, 3D mirror symmetry usually says that you have two gauge theories whose Higgs branch and the Coulomb branch are exchanged. And in some examples, the other theory could be non-Lagrangian theory, but suppose we assume both are gauge theories. But they usually don't say anything about the relation between the Higgs and the Coulomb branches. So we take one particular quantum field theory and we consider Higgs and the Coulomb branch of a single theory. So in that sense, the symplectic duality is different from 3D mirror symmetry. That is my understanding. So anyway, so this is various phenomena of relation between the Higgs and the Coulomb branches over a single theory. This is symplectic duality.
So the matrix attacking does it have a lower?
Yeah, this is interpolated. Yes, there's cross relation to relevantly.
What's your question?
Go back to this slides on flow variety.
Mm-hmm.
I remember there are three types of combination of three types, like orthogonal, I think that is
Mm-hmm.
very orthogonal.
Mm-hmm.
In the case of orthogonal, you always require that dimension to have the same parity, is that?
No, in general. That is one, maybe I should emphasize, thank you very much for this question. So this and, so you replace the group by Langland's dual group in the conventional sense, then the dual variety is either of two types. That is expectation. But if this SP is connected with odd, then naively, this is exchanged by maybe I should write. This is an interesting point. And this never appears in a single piece because it violates the Wheaton's anomaly cancellation condition. So this is SP of 2m. And this is SO of maybe 2n plus 1. So then if you replace naively by Lagrange's dual group, you get SO2m plus 1. And this is SP of 2n. So according to this notation, we should have this kind of variety. But this, so we always choose slice to some nilpotent orbit of Hooke type. So then we cannot allow these two different type of groups. For SPO, if both are SO and both are SP, then the right hand side doesn't make sense. But for this, we cannot. So the correct one is, so we should, in this particular case, we should take SP of 2m. So this reminds us that this metaplectic duality, but and maybe something to do with this, but, and also this is, as I said, this piece cannot appear because the Wheaton's anomaly condition says that if you choose a symplectic vertex and you take the sum of nearby vector spaces, then the sum must be even. And so if you combine it with the SO of odd in the other side also, then the sum becomes even. That is allowed, but this single piece doesn't. And when we define this Bow variety, if you have such kind of part, then you have this, and then you return back to SP in here. Then we add SP to it. So this is allowed. Well, yeah, that might be an interesting direction to consider.
By the way, is there any symplectic geometry or algebraic geometry kind of categorization for varieties?
I don't know. So I think, as far as I'm concerned, in general, Bow varieties are new varieties, which is nothing to do with nilpotent cone, this kind of variety, intersection nilpotent cone slice in general. So this is only examples, and if you study more different cases, then I usually get just also symplectic Bow variety, which I cannot identify with any known varieties.
Okay, perhaps let's stop for the question. Next talk is in 6 minutes.